In this video, we're going to discuss coequalizers. So we've already looked at equalizers in a previous video, and we showed that equalizers were a type of limit over a diagram with parallel morphisms, such as this one. And so what we're going to do is in this video, we're going to show the dual of the equalizer, we're going to define the coequalizer, and then we're going to look at a couple of examples related to the coequalizer. So to review, recall that the equalizer is a limit over a certain type of diagram, maybe call it D, where the equalizer is actually the limit over D, where D has two parallel morphisms in it. So here we have F1 and F2, both going from B to A, and we say that the equalizer, the limit over D, is the pair EE, capital E, little e, if, well, first we need the commutativity property, so this morphism here needs to commute with all of the morphisms in the diagram. So what does that give us here? Well, that means we need to have that F1 after E needs to be equal to F2 after E. And we also need the universality property, which says that for any pair X, X, like this here, which is another cone over D, that is, which commutes in the same way this one does, so we have F1 after X equals F2 after X, well then we must have some unique mediating morphism theta such that we can effectively factor this morphism here through our equalizer morphism. So there exists a unique theta such that we have E after theta is equal to X. So now to get the coequalizer, which is of course the dual concept to the equalizer, we need to do what we always do to get the dual, which is to flip every single arrow or morphism in the situation that we're talking about. So in this case, we have the parallel morphisms going from B to A. So in our case, we need the parallel morphisms going from A to B, right? We flip those two arrows. But then we also need to flip the arrows out here. So our equalizer morphism here went from E into B. So now our coequalizer morphism here needs to go from B into E, sorry. And similarly, our arbitrary morphism X here needs to go from B into X instead of X into B. So this is X again. And finally, our unique mediating morphism, theta, also needs to be flipped. So as you can see, we've flipped every single arrow. So now how can we write this out as a definition? So here we had F1 after E needs to be equal to F2 after E. So now we need to have the same chain but backwards. So E after F1 needs to be equal to E after F2. So this is our commutativity property for the equalizer. So that is E after F1 equals E after F2. And what would our universality property be? Well, it would be, or I guess co-universality property in this case, it would be that for any pair X, X, such that in this case they commute but this way, so X after F1 equals X after F2, we need to have that there exists a unique mediating morphism theta, which goes from, in this case, E into X, such that this triangle commutes again. But in this case, we're going first through our coequalizer and then through our mediating morphism. So we have X equals, see, it's just this one flipped. theta after E. And of course, if the equalizer is the limit over D, then the coequalizer similarly needs to be the colimit over D. And that's that same pair, E, E. Except in this case, obviously, E goes in the other direction. So in terms of a definition, we're effectively done here. There's not a whole lot more to say. We've put in a lot of work already to understand the equalizer and how it behaves, so it's not super surprising to create a definition where we just flip all the arrows within our concept, which in this case was the equalizer. So we'll just keep this definition handy over here, and we'll actually just start right away to look at some applications. So obviously in most cases the simplest example to use is just how this looks in set. So let's start with that. What does the coequalizer look like in the category of sets? So let's suppose we're in the category of sets now, and we've sort of recreated this situation here with some arbitrary example sets. And let's first focus on this property here. So we need to have the commutativity of these two chains. And so that gives us that E after F1 has to be equal to E after F2. So now that we're in set, we can talk about the elements within sets, and we can talk about how they map under different set functions. So let's suppose that the blue arrows here represent the mappings of F1, and the green arrows here represent the mappings of F2. So another way of stating this condition is to say that E left equalizes F1 and F2, right? In equalizers, we talked about right equalization, how E had to right equalize our two parallel morphisms. But now we have E on the left-hand side, which means it gets applied after F1 and F2, and so it equalizes on the left. And so what does that mean? Well, it means that we either have one of two situations. Either F1 and F2 agree on what they send this element, say. They both send it to the same element, so we're good there, right? Because if we map this one, say, to here, well, we know that a function will always map a single element to the same element. So if they both agree on what they send this element to, then they're definitely going to agree on what this chain sends that element to. But the other situation we could have is that they diverge. They don't go to the same element. So say for the second element here, F1 sends it to this element and F2 sends it to this other element. Well, what do we need to have? We need to have that these must both map to the same object, right? Because if these mapped to different objects, then these chains would no longer be equal. If I followed E after F1, I would end up in a different place than if I followed E after F2. So this may be our function E here. And another way to think about this is to say that there are certain elements within this set B that we need to force to map to the same element under E, right? There's certain groupings in here where that entire group needs to all map to the same object. Namely, when F1 of A, say, in A, and F2 of A diverge. If that's the case, then we need both of these elements to both map to the same thing by E. So we'll look at this a little more rigorously in a second, but let's just think about this intuitively for now. We're trying to group elements in B, or another way of saying that is we're trying to associate pairs of elements in B. Or another way would be to say that we want those elements to stand in a certain relation to one another, right? So giving the game away, that's how we want to model this mathematically. We want to say that, and this isn't going to be very rigorous, like I said, let's just look at it intuitively for now. So B1 is related to B2 if we want to force E of B1 to be equal to E of B2. Right? If we want to force them to be constant by E. And when do we want to force that? Well, say in this first case, both F1 and F2 map this element to the same element. So the only restriction we need is that this element always needs to map to the same thing under E. But that's obvious, that's just how functions work, right? E always maps this element to this same element. So we can always say that B1 is related to B2 if B1 is equal to B2, right? We always want the same element to map to the same element. It's obviously just a definition of the function, but that's what we want, right? We want to force it, so we will say that. Well, what's the next situation? Well, it's the one we just talked about. These diverge. And so in that case, we need to have that these two elements, which are the image of F1 and F2 respectively of this element here in A, we want to force those to go to the same element by E in capital E. So how do we do that? Well, we say that B1 is related to B2 if B1, B2 is equal to F1A, F2A for some A in A. Right? If there's some element A that maps to two different things, F1 and F2, and by the way, we don't need to mandate that these are different, right? Because it still applies even if this is the same. It would just be B, for example, say this is B, it would just be B equals F1A, F2A, because they both map to the same thing. So in this case, we just want to say that B1, B2, this grouping here, is two elements that are mapped to by the same element in A by F1 and F2 respectively. And the last condition that we want is that, say, for example, in this situation, so we haven't even fully drawn this out yet, because say in this situation, we have A and A, say this is A, and it diverges, and then we also have, say, A prime that diverges, or something like that, but they diverge in such a way that two of them collide, right? This mapping from F2 and this mapping from F1 both map to the same element. Well, if that's the case, then we need all of these images to all map to the same thing, right? Because these are related, and these are related, and these are equal. So we need all of these three to all map to the same thing, right? Hopefully that makes sense. So another way to say that is if B1 is related to B2, say B1 is related to B2, and B2 is related to B3, say B2 is related to B3, right? Because these diverge and because these diverge, then we need B1 is related to B3 also. They all need to map to the same thing. So do you see, hopefully, what those three conditions give us? They give us, in a very non-rigorous way, the fact that this relation that we've defined is an equivalence relation. Because we have any element, this one here, any element is related to itself, that's reflexivity. If B1 is related to B2, then we have B1, B2 equals F1A, F2A for some A and A. But then B2 is also related to B1, right? Because this set ordering doesn't matter. Ordering doesn't matter in sets. So B1, B2 is equal to F1A, F2A. Well, then B2, B1 is also equal to F1A, F2A, right? So those will be related, and that gives us symmetry. And then we have that B1, B2 being related and B2, B3 being related gives us that B1, B3 must be related. And so that's called transitivity, right? So this is reflexivity condition, this is symmetry condition, and this is transitivity condition. And so our sort of non-rigorous definition here, if we can somehow make it rigorous, will represent an equivalence relation on B. Now, one thing we might ask ourselves is, we're talking about arbitrary functions f1 and f2 here, so there's nothing to say that f1 and f2 are surjective, so there may be elements in B here that are not mapped to by either f1 or f2. They're not in the range of f1 or f2. So if that's the case, then what happens with this element? Well, it's no big deal, right? We don't need to force it to do anything, effectively, because we're not worried about it, because we're only worried about the mappings that f1 and f2 give us. So say we have some element here, doesn't matter, we can just map it to this one as well. But it's not in relation with those other ones because it's not something that we need to force, right? It can basically just map to whatever it wants, and it won't mess up our equality condition at the top here. So how can we make this definition rigorous? Well, we have a semi-rigorous definition in this line here, this middle line. So maybe let's just highlight that. B1 is related to B2 if B1 is equal to B2. Okay, that's totally rigorous, nothing wrong with that. B1 is related to B2 if B1, B2 equals F1A and F2A for some A and A. Okay, well that's also perfectly rigorous. So the only issue is this transitivity rule here, right? We don't really have a rigorous way of stating this because we're just saying, well, these are related and these are related and these are equal, so we want to force these, right? That was our definition. We want to force them to be equal. But what we can just say is, let's just take this rigorous definition and let's just add transitivity, right? We can always add the transitive closure of any relation. And if that relation is both reflexive and symmetric, then the transitive closure of that relation will also give us the transitivity property that we need to make it an equivalence relation. So let's rewrite this rigorously. So now we have an equivalence relation, so we can say that B1 and Bn are equivalent by tilde if B1 is equal to Bn, so that means every element is always in a grouping with itself. That's reflexive. Or B1 Bn equals F1 of A, F2 of A for some A and A. So that's the diverging case, and this is an obviously symmetric property. And then we have the transitive closure of this relation in the first line. So if any finite sequence of B1 through Bn's exists such that each one is equivalent to the next one in the sequence, then we must have an equivalence relation, and we also must have that they are in the same grouping because they all need to map to the same thing by E. And so that leads us into our next observation, which is that because we have an equivalence relation, we have a partition, right? Anytime we have an equivalence relation, we have a partition and vice versa. So in this case, what will be the partition? Well, this one needs to be in a grouping by itself. Then we said these two need to be in a grouping, and these two need to be in a grouping, but because these two are equal, we need to have all three of these in a grouping, right? So this is where our transitive property comes into play. And for any element not in the range, I guess, of F1 and F2, we can just group it by itself as well, because we don't need to force anything with that one. So what does it take to satisfy this property here, the first property in our coequalizer definition? Well, we need to have that E is constant on the equivalence classes of this partition, right? Of the partition created by tilde, which is denoted this way, right? B divvied up by tilde. So if we have E constant on all these equivalence classes, which is exactly what we have here, right? Constant, constant, and these three are in a grouping and they're all constant as well. So this is what we need to have this property. And if we have this property, that means we have a cocone. So we know what it takes to be a cocone over D. So now, in order to find a coequalizer, we need to find a cocone that also satisfies this co-universality property. So again, if EE is our coequalizer, our potential coequalizer that we're looking for, then we need to have that for any other cocone, XX. And what would it mean for xx to also be a cocone? Well, it means that x, the function, also needs to be constant on all of these equivalence classes, right? It's the same property. So if we can find another cocone with an x that satisfies that property, then we need to have exactly one morphism going from e into x, or one set function going from e into x, such that this triangle commutes. That is, x equals theta after e. Well, there's one thing we can say right away about this set function e, which is that it has to be surjective. If you want, you can pause the video here and try to figure out why that is. There's a couple ways we can see it. The first one is sort of the more categorical way, which is that in the video on equalizers, if you remember, we proved that equalizer morphisms are monic. You can go back and look at that proof if you want. I'll link the video, but if equalizer morphisms are monic, then what is the co-theorem to that, basically, that we get for free in category theory? Well, we just have to take the dual concept of every categorical concept in our sentence, basically. So we have to say that coequalizers are epic, or that coequalizer morphisms are epic. And what does it mean to be epic in the context of set functions? Well, it means that it's surjective. So that's one quick way we can see it, but we can also sort of prove it to ourselves, which is to think, if I had another cocone here, say xx, and maybe say x again has two elements, and maybe just for sake of argument, we can say that all of these elements all map to the same one. So it has to be constant on the equivalence classes in order to be a cocone, but let's just make it constant across the whole function. So let's say this one maps here, and this one maps here, and this one maps here, where this is little x, and we've just drawn the mappings from the equivalence classes, right? So that means all of the ones in here all map to this same element in x. Well, now if we suppose that e is no longer surjective, so let's say instead of mapping to this top element, now this top element in b gets mapped to the same one as all the rest of them down here. And now this one is not mapped to by anything in E. Well, it's pretty easy to create a mediating morphism for this, right? We just map the one that everything collapses to here into the one that everything collapses to here, right? That is definitely going to make this triangle here commute, that's for sure. But what's the problem? It's not a unique mapping, right? Because this chain doesn't involve, this chain here of E and then theta doesn't involve this element here. So this element is always going to be free to be assigned to anything we want, right? If we assign it here, then this commutativity still works, right? Because it doesn't even involve this element. And if we map it here, same thing. So effectively, if we ever have an element that's not mapped to by E, then it can always be mapped to anything in X by theta and could still satisfy this commutativity property. So it will never be unique. So E definitely has to be surjective. But there's actually one more condition we need, which you may have noticed during our previous discussion even, which is, let's say if we switch this up a little bit and suppose instead that X has 3 elements in it. So we have now this is X with 3 elements in it, and instead now each one maps to its own element each equivalence class maps to a distinct element in X. Well, if that's the case, then what's the issue here? Well, there's only two elements in E, and we need a mediating morphism that's going to go from E to X, where this is little x, such that X equals theta after E. But that's not going to be possible, right? We're only going to have two options here to map to, and we need all three to be able to map to. And so we're not going to be able to do that. So what do we need? Well, we need E to have at least as many elements as X, right? So I need to add a third element here to E. But not only that, I need something mapping to it as well. Because if this collapsed like this, first of all, it wouldn't be surjective, which would ruin our first condition that we just talked about before. But also, now I'm still in this composition of E and theta. I'm still only mapping two elements, right? So we also need at least one arrow mapping from one of these equivalence classes to this one. And because these three all need to be constant, we would need to move these two as well. So now this middle equivalence class, everything maps to the middle element, and this bottom one still by itself maps to the last element. So now I can create the mediating morphism, and I need to do that by making sure that the triangle commutes, right? So this one needs to land up in the same spot as this one. So that would be like this. And then this middle equivalence class all goes to here, and this one all goes to here. So same thing there. Need to have this one mapping here. And finally, same thing for the bottom. This one maps to here, and this one maps to here. So we need to line those up to make the triangle commute. And not only that, but this is going to be unique, right? There's only one way to assign all these elements such that it lines up with the way they're all mapped by X. So what we see is that in order to satisfy this second condition, the co-universality condition, we need two things to be true. First of all, we need to have that E is surjective. If it's not surjective, it's not going to be a coequalizer morphism. And here's where we have to be a little bit careful, because it might be tempting, based on this discussion, to say, well, E also has to be injective. But that's clearly not true, right? Because these groupings all need E to be constant on them. And so they need to all map to the same thing. So there's definitely going to be times where multiple elements in B are all going to map to the same thing in E. So for sure, E is not going to be injective. So what's the correct way to phrase this second property here? I mean, we discussed this property, and it certainly looks like it's involving injective morphisms, but we know that E itself can't be injective. So what's the correct way to phrase this property? Well, remember when we defined X here, what we said was because X has to be constant on these equivalence classes, we don't actually need to draw an arrow for every single element. We can just draw one arrow from the equivalence class itself into X and basically call it like a placeholder, right? And that just means we said that every element in that equivalence class maps to whatever that arrow points to, that single arrow. Well, what we were doing implicitly there was we weren't mapping B into X. We were actually projecting the elements of B into their equivalence classes and then just mapping the equivalence classes, right? It sounds so simple when you draw it like this, but mathematically, we need to say, well, first, we need to take the canonical projection, which goes from B into the set of equivalence classes over tilde, and that just takes a B and B and maps it to the equivalence class that B is a part of under tilde. And then we need to apply the mapping to x. So actually this x that we drew here was actually more like this kind of thing, going from the equivalence classes to x, right? Rather than from b to x. And this mapping is well defined precisely because these are constant across that equivalence class, right? So it always makes sense that we can project the entire equivalence class because they're all going to agree. So we just pick the one that they all agree on. So maybe rigorously we can call this x tilde. So this is not the mapping x, which does actually go from b to x. It's the mapping x tilde, which just simply takes the equivalence classes. So x tilde of an equivalence class of an element b will just give you back what x of b would have given you, right? And again, that's well defined because these are always constant, so it always makes sense. There's only one that we can assign it to, which is the definition of a function. So which mapping needs to be injective then? Well, it's e tilde, right? That's exactly what this argument was saying here, right? We basically need to have one element dedicated to each grouping, each equivalence class, when we map it by E. Otherwise, we could always create another cocone X that had more elements in it. So say this only had 2 like we had before and one of these collapsed. We could always create this one with 3 in it that would make the mediating morphism property impossible, which we just saw earlier, right? So it's E tilde here that needs to be injective. So that's actually the second property that we need. We need to have that E tilde is injective, where E tilde goes from b divvied up by tilde into E and is defined by E tilde of an equivalence class gives you whatever E would have mapped the element of that equivalence class to. But there's actually something else we can say about E tilde, which is that notice that E is surjective and the range of E tilde is going to be the exact same as E, right? Because it's just like, you can think of it as just like collapsing all these into one arrow, right? It doesn't change what gets pointed at in E in the codomain. So we have actually that anytime E is surjective, E tilde must also be surjective. And so what does it mean if E tilde is both injective and surjective? Well, it means that E tilde is a bijection, right? E tilde is a bijection. So we can actually look at it like this. And this is actually a crucial fact because this tells us exactly what our coequalizer is. So if you're looking for a slightly more advanced exercise, pause the video here and figure out why this statement here fully defines what our coequalizer is. Well, it's because E was our coequalizer object, right? And we know that E is in a bijection with b divvied up by tilde, the set of equivalence classes here. But in the category of sets, a bijection is an isomorphism, and limits, therefore coequalizers, are only determined up to isomorphism. So if there's an isomorphism here between the set of equivalence classes and E, we can actually just say that E is b b divvied up by tilde, right? The object part of our coequalizer is just the set of equivalence classes when we divvy b up by tilde. And now we just need our coequalizer morphism. So we need some sort of morphism, or function in this case, going from b into our coequalizer object, which we said was b divvied up by tilde. And so what's the obvious fill in the blank here? Well, it's just the canonical projection, right? So just to quickly confirm that, we know that E after F1 is going to be equal to E after F2. And if we replace this with rho now, our canonical projection, then we have that rho after F1 is equal to rho after F2. Well, yeah, we know that because always F1 of A and F2 of A need to map to the same equivalence class. So if we take the canonical projection of either one, it doesn't matter. We're going to end up in the same equivalence class. That was the definition. And at the same time, if we have some other cocone over D, then it has this same property where it must be constant across these equivalence classes. So it doesn't matter if we first project into our coequalizer object here, which is now effectively these red circles here, right? Just transplanted over here. B divvied up by tilde. It won't matter because the fact that they're constant uniquely determines what theta has to send each element to, right? Theta has to send each element to the same thing that that equivalence class is being sent to by x. So that's the end of this exercise. We found the coequalizer in the category of sets. So let's just sum it all up to conclude with this exercise. Let's say that we have two parallel morphisms, F1 and F2, both going from A to B in a diagram D. Well, then the coequalizer, which is the co-limit over that diagram D, is the object B divvied up by tilde, that is the set of equivalence classes when we divvy up B by the partition created by the equivalence relation tilde, and the canonical projection, which goes from B into that set of equivalence classes. And the equivalence relation tilde that defines this is B1 is equivalent to B2 if B1 equals B2, or B1, B2 is the same as F1A, F2A for some A and A, or the transitive closure of this relation here. So it sounds like a bit of a mouthful when we state it all together like this, but just remember that the key insights were that the cocone morphism for any cocone over our diagram D has to group together these elements in B based on how F1 and F2 map them, and then it needs to be constant on those groupings. And then we also found out that we have a uniquely determined function, which we called, in this case, x tilde, for any morphism or any function going from B into x by first projecting it into the equivalence classes and then just looking at it from there. In a way, it sort of simplifies the situation because there's only one arrow for each equivalence class instead of as many arrows as there are elements in that equivalence class, but they all still map to the same thing, so it's still a well-defined function. We'll finish up with one quick exercise to show what this looks like in the category vect K, which is the category of all vector spaces over a given field K. And just recall that vector spaces are of course sets, and so this entire discussion will apply as well to the example that we discuss next. So as a final exercise, we're going to prove the following theorem here, which says that in vect K, a morphism is a coequalizer if and only if it is epic. So what does that mean? Well, basically a linear transformation is a coequalizer if and only if it's surjective. So we saw already this direction, right? Any coequalizer morphism in any category has to be epic. So we just need to prove the other direction. We just need to prove that if a morphism is epic, or if it's a linear surjection, then it also needs to be a coequalizer morphism. So let's fix a field K for our category vect K here, which again is the category where the objects are the vector spaces over the field K, and the objects are the morphisms are linear transformations between those objects, between those vector spaces. And so we fix our field K and take a transformation T from, say, V into W to be surjective. So we have an epic morphism in the category of vector spaces over K. So if we look at our diagram here, we're basically saying that any surjective linear transformation has to be a coequalizer. So let's just fill this in for our diagram. So E now becomes T, right? Because that's our surjective linear transformation, which is epic and therefore needs to be a coequalizer according to the theorem. And this is going to go from the vector space V to the vector space W here. So basically what we need to find are two linear transformations, both going from some vector space over K. So we don't know what this is yet. This is going to be like a fill in the blank. And it's going to go from that vector space to V. And they're both going to go in that same parallel direction. And we need to show that T is the coequalizer of those two morphisms, or those two linear transformations. So before we try to figure out exactly what F1, F2, and this blank are, let's just think about the discussion we just had in the category of sets. Well, we said that the coequalizer was basically an inclusion or a projection from our domain B of our coequalizer morphism into basically a quotient of that domain, right? It was B divvied up by tilde. It was taking the elements of B and then divvying them up into groups and then mapping each one into the group that it belongs to. So now vect K is a set-based category, right? It's a set-like category. So that means there's a forgetful functor from vect K into the category of sets. So that entire discussion has to also apply to vect K. And if that's the case, we know that we have to go from our vector space V into some sort of quotient over V. Well, what's a quotient that we know is a vector space? Because remember, this also has to be a vector space as well. So what's a quotient over V that we know is a vector space over K? Well, we can talk about V divvied up by the kernel of T. Right? This is a vector space over K, where maybe let's say capital K is the kernel of T, and remember the kernel is just all the vectors in V that get mapped to 0 in W, right? And the vectors of this vector space are the equivalence classes that represent the cosets of K, right? The cosets of the kernel. So when we add elements in V or vectors in V to vectors in the kernel, we end up with a set of equivalence classes, and we can identify any vector v by just mapping it into the equivalence class that it belongs to, right? Just exactly the same way we did in set. But not only that, the first isomorphism theorem tells us that v over k is actually isomorphic to the image of t. Right? That's what the first isomorphism theorem says. For any linear transformation from v to w, the image of t is isomorphic to v divvied up by the kernel of t. And what is the image of t? Well, it's just w. Right? Because this is a surjective map. So if it's a surjective map, then everything in W gets hit in the image, right? Everything in W gets mapped to, so it's all in the image. So these are actually just the same. There's nothing in W that's not in the image. So we can say that W is isomorphic to this quotient space here over the kernel, and that makes perfect sense in the context of the category of sets that we just talked about. And furthermore, T, if we want to call it this, we can think of it sort of like T tilde or whatever we want to call it, goes from V into V over K, just like our projection, canonical projection, went from B into B over tilde, right? It's the exact analogy in vect K. So hopefully this informal discussion is enough to convince you of the intuition behind it. But as a final exercise, we can show that this is actually the kernel of T, K, which, remember, forms a subspace over K because the kernel is called the null space, right? It's a vector space. And F1 is going to be the inclusion map from the kernel into V. So basically, all the elements that map to 0 under T just pick themselves out in V. And the 0 map from the kernel into V. So that's just where it takes every element of the kernel and just maps it all to 0. So you can probably see why it makes sense that those would be coequalized. So to write that, we have F1 is going to be equal to the inclusion map from K into V, from the kernel into the domain of T, and that's defined by the inclusion of K is just equal to K, and obviously that's a K in K, that's not the K of the field. Probably should have chosen a different letter. But and then F2 is just the 0 map from K into V, and that's just where it takes any K in the kernel and just maps it to 0 again for K and K, not to be confused with the K of the vect K here. So you can try that as a final exercise, and that concludes our discussion on coequalizers.